Let's talk about the classification of these elementary particles. And if we have to generalize these elementary particles, I mean, there are basically a large number of these elementary particles, including mediating particles between two particles, whom we call as quantas, the mediating particles. We call them quanta of forces. And these elementary particles have different characteristics, and they interact with each other through different types of interactions. So, so what is important here is that we want to have some basic classification of these elementary particles. And the elementary particles can be classified broadly into two categories. The first one I would like to say is quanta force. Quanta of force. And the second one is matter, or material particles, or material particles. So now let's start with these quanta of force kind of particles. I mean, there are four types of interactions in nature, and we know what these four kinds of interactions are. One is gravitational interaction, electromagnetic interaction, strong interaction inside the nucleus, and we have a weak interaction. I mean, two particles or objects, they interact, they exert force. If you have two particles, what they do is they interact, they exert force on each other. And this force is a result of exchange. It's a result of exchange of particles, what we call as quanta of forces. So it means two particles are objects. They interact with each other via the particles. And that is the exchange between the interacting particles of the objects. So the particles which is exchanged between these two particles, between these two interacting particles, they are called mediating field particles. They are called mediating field particles. Or we call them simply quanta of force. Now, the quanta of forces involved in the interaction, they are never seen. They're never seen experimentally. They are never seen. Hence, they act as virtual particles. Virtual particles. Now, we have different types of quanta of force. So, if I have to go with it, we have a different quanta of force, or we call them mediating field particles. They may also be called as virtual particles. Now, the quanta of force of gravitational interaction is a graviton. So it's not discovered yet, but we call it graviton. Okay, so this is a quanta of force particle, and photon is a quanta of force of electromagnetic interaction. So we have another mediating particle here as photon. So this photon is the mediating field particle of electromagnetic interaction. And then we have gluon. And this gluon is a quanta of force of strong nuclear interaction. And the quanta of force of weak interaction, we have for that W plus minus and Z0 bosons. They are bosons. So this is a brief classification of quanta of forces, where the mediating particles, in case of gravity, are gravitons, and gravitons, they are purely theoretical in nature. We have not been, nobody has detected graviton experimentally. And then we have another class in electromagnetic radiation, whom the mediating particles here, we have photons. In case of nucleus, the strong interaction that we have, that interaction is through the quanta of field, the quanta of force, or the mediating field particles, or the virtual particles here are gluons. And in case of weaker interactions, we have quanta of forces as Z plus minus and Z0. They are all acting as bosons. Now, let's talk about the matter particles. Now, the elementary particles that we have, they are the building blocks. They are the building blocks of matter. They are the building blocks of matter. And these building blocks of matter, the particles, the elementary particles, we call them as matter particles. They are called as matter particles. Or we may simply call them as material particles. These matter particles are grouped into two different categories of families. And depending on their properties, depending on the type of interaction they are involved in with other elementary particles. Now, these two categories that I would like to approach here for material particles, we have the first one is leptons, and the second one is hadrons. Now, talking about leptons, these leptons are elementary particles having half-integral spin. So they have a spin of 1/2 cross. And they obey, because they are fermions, so they obey Fermi-Dirac statistics. What we, in symbolized form, call as FD statistics. And leptons, they are of two types. I mean, these leptons, we have charged leptons, and we have neutral leptons. Now, charged leptons, they interact in electromagnetic manner. They interact with each other with respect to the electromagnetic interaction, as well as weak interactions. And these neutral leptons, they participate only in weak interactions. They participate only in weak interactions, and charged leptons, their participation is both in weak interaction as well as in electromagnetic interaction. Now, talking about hadrons, I mean, hadrons are the elementary particles that have integral spin. Integral spin. And if they have integral spin, certainly what they obey is they obey Bose-Einstein statistics. They obey Bose-Einstein statistics. And this Bose-Einstein statistics is symbolized as BE statistics. Right. So that's why these hadrons, we may also call them as bosons because they have integral spin. And these hadrons, or you may call them as bosons, they participate in all the three interactions. I mean, they participate in strong interaction. They participate in strong interaction. They participate in electromagnetic interaction, and they also participate in weak interactions. So what should I say here is that we have two categories of these matter particles, and these matter particles are as leptons, and the other category is as hadrons. Now, moving on to antiparticles. Now, almost in the early 20th century, we have relativity and quantum mechanics, and these two fields came in action. They came into existence. Relativity and quantum mechanics. And these two fields came in existence in 20th century to describe the microscopic world. And it was Paul Dirac, whom we call P.A.M. Dirac, in 1927. What he did, he merged these two concepts, the concept of relativity and quantum mechanics, and formed a new mechanics, what's called as relativistic quantum mechanics. And later, in 1947, this relativistic quantum mechanics unified with Maxwell's theory, and what it described is called as quantum electrodynamics. Call it quantum electrodynamics. And this is purely symbolized as QED. Now, Dirac's equation that Dirac deliberated for a free electron with energy given by this relativistic formula is that E square is P square C square plus m naught square C to the power of 4. Now, this equation has two solutions because if we have write down E, so it's under root of P square C square plus m naught square C to the power of 4 plus minus. So what Dirac did, he introduced the concept of antiparticles corresponding to this negative energy. Antiparticles corresponding to this the negative root of energy that we have here. And in the solution, the negative energy solution that corresponds to these antiparticles. Now, what he did, he postulated that for each particle there corresponds an antiparticle. So you have a particle, you have an antiparticle, having the same mass as that of the particle, but having charge opposite. Having opposite electric charge to that of the particle. This is what Dirac postulated. The antiparticle of electron was named positron. So if we have electron as a particle, its antiparticle is positron. This standard notation to represent the antiparticles is basically a bar. If you put a bar on the quantity, it will be a representative of the antiparticle over the symbol of that particle. However, in some cases, this antiparticle is represented by specifying the polarity of the charge, as in case of the electrons that we can see here. Now, if you take an example of the proton, now if I take the particle P as proton, its antiparticle is P bar. But in case of electron, the antiparticle is represented by E plus. And it was in 1932. It was in 1932 that C.D. Anderson he discovered the positron. What was predicted by Paul Dirac, it was experimentally detected while studying the track left in a cloud chamber by cosmic ray particles. Now, the discovery of this positron, certainly it provided the first experimental proof. It was proof of the relativistic quantum mechanics. The relativistic quantum mechanics. And talking about Wolfgang Pauli, Pauli postulated the existence of neutrinos. It was Pauli. And he postulated the existence of neutrinos. And antineutrinos as nu bar, to explain the continuous spectrum of beta particles that we have discussed somewhere, and a particle identical to the proton except for negative charge called as antiproton. It was discovered by the later pupil, and I believe the name was Serge. This antiproton was created by bombarding the copper target with a proton of energy nearly 5 to 6 giga electron volts. So in a reaction, proton plus the energy of 6 giga electron volts, what it does, it gives three antiprotons. It gives 3 protons and 1 antiproton. It is proton, but its charge is negative. So this P bar represents an antiproton. As soon as this antiproton slows down in an experiment, it is annihilated by a proton. So it's annihilated, it converts into energy. Therefore, thereafter, antineutron was discovered. So later on, after this, what we have is the pions. So later on we have pions and muons. And they were discovered with both particles and their antiparticles and their corresponding antiparticle species. Now, the world consisting of particles is called matter. So we call it matter. And that consisting of antiparticle, we call that as antimatter. So we have two worlds, the world of matter and the world of antimatter. Now, for example, if we take an example of an electron and positron orbiting around their common center of mass. I mean, if you have a positron and you have an electron, now they are orbiting on their common center of mass. They form a bound state, and this bound state is called as positronium. Now, it is the lightest hydrogen-like atom bound by electromagnetic interaction. And this lightest hydrogen-like atom is called as antihydrogen. We call it antihydrogen. However, if the matter and antimatter comes into contact, then the particle and the antiparticle, they annihilate, and the mass of the annihilating particles is converted into the energy. And for that, we have a simple reaction, electron and positron, giving us two gamma ray photons. So we can say here that the matter and antimatter, they cannot coexist with each other for a long period of time. Now, moving on from here, now talking about some observational point of view for this antimatter. Now, when the high energy in the form of electromagnetic radiation, we have, say, gamma ray, we have a gamma ray photon, okay? And when it interacts with matter, a particle and its corresponding antiparticles are created. Okay, it interacts with matter, and we have a particle and its antiparticle. Now, this phenomenon is called as, we call it pair production. Or we can also call it as pair creation. And it can be simply represented by having a gamma ray photon with matter and interacting with matter, giving us electron and positron. So here what we have is the conversion of energy into the matter. So you have energy and you have matter here. So where this E negative is an electron and E positive, we have this as positron. Now the electron-positron pair production occurred that occurred in Anderson's experiment, where high energy cosmic rays that had hit the lead piece in a chamber, what's called as cloud chamber. Now, when uniform magnetic field was applied perpendicular to the plane of this, so when you had a magnetic field perpendicular to the plane of this cloud chamber, electron and positron moved in circular paths of the same radii, but in opposite direction. So suppose this is an electron, we have positron in opposite direction. So electron and positrons orbiting around their common center of masses formed a bound state known as positronium. Or what it is called is antihydrogen. And the reverse of pair production phenomenon is known as pair annihilation. It is also possible when electron and positron moving in opposite direction, they come in contact and they annihilate, and the mass of these annihilating particles is converted into the energy in the form of an electromagnetic radiation. And we have both the processes here, the process of formation of energy from the matter and the process of forming of matter from energy.